Well, good afternoon, everybody. This is Bob Hayes. I'm chairing this webinar. I'm pleased to welcome you along to an event. We're looking at strategies and tactics to decarbonise heating and cooling in the process industry. This is the first of a number of webinars we're going to run, so we hope you're going to enjoy this one and will join us on future events. We've got a couple of speakers for you today. The first one who's going to be speaking is Professor Stuart Scott, who's the Professor of Energy and Thermodynamics at the University of Cambridge. Stuart's the director of the Energy Technologies Masters Programme and has got a lot of experience in terms of energy generation and particularly the abatement of CO2. And he's written a book on the topic. And then we'll be hearing from Daniel Wells, who's the National Consultant Specialist in Spirax Sarco. Again, a huge amount of experience behind him. He's worked extensively across the UK and into the Republic of Ireland across a range of different industries and different applications for heating, process heating. So rather than listen to me for too long, I'll hand straight over to Stuart.
Okay, thank you, Bob. So welcome. As I'm Stuart Scott. I'm from the University of Cambridge and I lead our master's programme on energy technologies. And that gives me a sort of overview of the energy system that we all operate in. And so I thought I'd start this series of talks by just giving an overview of our energy needs and also where the process industries and process heating fits in with that. So first thing I'm going to do is show you the UK energy flow charts. This is data that is taken from the UK government. This is produced every year, and I've used the 2021 data because it's got some particular data I need later on the top. But what you can see is on the left-hand side, you can see all the sources of power. So over here, we can see, we have natural gas coming in, we have coal, electricity, and the thickness of the bar in these charts represents how much energy is coming in. And then we can follow each bar through and we can see where it ends up. So for example, we can see how it splits into industries, transport and domestic. And what I'm going to do is take you through this chart and see where process industries fits in on this. But to do that, I'm going to have to simplify it a little bit, just so I can break things down. So I'm going to draw a boundary around it so I can just see our own natural gas. So I'm going to exclude imports. I'm going to include the electricity that we generate ourselves, so renewables and bioenergy, and also our own petroleum usage for transport. And so if I simplify that chart, and this is my chart, we can see where energy comes and goes in the economy. So you can see, for example, we have 69 million tonnes of oil equivalent of primary gas coming in. Most of it goes to sort of space heating. And you can see that if we follow the bar through, quite a bit goes through power stations and then is used for electricity generation. And you can see eventually we end up with the electricity 17, well, it's actually not 17, but we end up with a reasonable amount coming through to industry. And equally with gas, you can see direct firing of gas contributes to our industrial use. So overall, industry contributes about 17 kilotons of oil equivalent. And the nice thing about these charts is you can use the width of the bars to look at the orders of magnitude of the energy involved. So rather than quoting million tons of oil equivalent, you can see how much of the UK energy system is involved. Now, if we break apart the industry section, we can break it down into sectors. And this is the reason I use the 2021 data, because the UK government also publishes energy use data by industrial sectors and also by use. So we can actually see what kinds of things the energy is used for. And you can see that electricity goes into pretty much every sector, gas goes into every sector, and then we have these use categories: refrigeration, low temperature process, lighting, other. We've got separation, space heating, motors we're not so much interested in. And here, what we want to do is really zoom in and have a look at these processes here that we're really interested in this seminar series. So here we have low temperature processes. So this is processes that typically heat of less than, say, 200 degrees Celsius. It might be steam, it might be ovens, and we can see that this is heavily used by food and beverages, chemicals. We also have another category here, which is high temperature processes, and this is a very different kind of heating. So here we're talking furnaces, and here we're doing direct firing of fuels and also using a lot of electricity. And then finally we have drying and separation, which consumes a huge amount of process heat. Now, the nice thing about all this is you can see immediately that in the UK, we get most of our process heating from either gas firing or through electrical heating. And if we just zoom in on the particular ones that are of interest to us, we can see that, well, as I say, the ones that I think we're talking about today with low temperature process heating is steam, but we can see the magnitudes of these compared to how it compares to the rest of the economy. So if we zoom back out, we can see that process heating is really quite a significant part of the UK energy system, but it's also not the biggest sector. So this is interesting in that if you think about the kind of changes that are going to have to be made going forward as we decarbonise, although we will have to decarbonise process heating, it's not going to be the thing that breaks the back of the transition. So it's within the, not noise, but it's certainly not the thing that's going to be the most difficult thing to change. So if we're going to be decarbonising the whole of heating, for example, or natural gas use elsewhere, then really we should be able to decarbonise things like process heating. So how do we do it? Well, going forward, really the only way to decarbonise is either bioenergy, which I'm not really going to talk about, or electrification. And the problem with electrification is you lose, I'm going to use the word exergy here, but electricity is really high quality energy. So if you use it for low temperature heating, thermodynamics, or what we teach our students, is that this is not such a good idea, because we could have got more stuff from our electricity. So for example, we could have used a heat pump instead of using the electricity directly. Now, again, going forward, that may or may not be a valid argument, because it turns out that cost is going to be the thing that dominates over thermodynamics. And the key thing is whether electricity itself is going to be expensive. And this is something I'll talk about in a moment. So at the moment, electricity is much more expensive than gas per unit of energy. And also, you tend to get both high capital costs when you use electrical heating for things like furnaces, because you need a large number of heating elements compared with direct fuel firing. So in general, electrical heating at the moment is probably the more expensive option. However, going forward, there's always the argument that we're going to have so much renewables that in future electricity is going to become cheap. In fact, the idea that of free renewables is something that comes up a lot if you think about how we'll be using energy in future. But the real question is, will this be true going forward? So here you have some work that one of my master's students did. They took the black line here is our electricity demand for a particular year, and they've scaled it forward to 2050. And this is using the electricity grid's own scenarios, community transitions, and just switched off our gas power stations and replaced them with the kind of order of magnitude amount of wind and solar that we'll have running. And so, for example, you see earlier on in the year, you find that you have enough energy, and there are days when you have quite a lot of excess renewable. So on this axis here, we have settlement period, and each one of these little peaks that you see oscillating, each one of those is a day. So this is a quarter, the first quarter of the year. Now, what we also see is that there are significant days where you have not enough energy. And so there are two things here. First of all, we're going to potentially have lots of renewables that's producing too much energy, but you also get significant periods, and you're talking multiple days where there's insufficient energy or insufficient electricity provided from renewables to provide free green electricity. And so this means that we're potentially going forward into a situation where we're having to employ energy storage. And if that's the case, this idea of cheap electricity is something that's going to be more difficult to justify, because storage is generally quite expensive. So the second point is that here we've got a rather large amount of renewables, which means our renewable generation capacity is effectively being curtailed and turned off. And so here you've got quite an expensive lot of electricity from renewables, because the capital isn't being used effectively. So this is something people are worrying about going forward. Today, of course, we don't have this problem because we're firing with natural gas in our power stations. We can always meet demand. But in future, when we're using electricity to decarbonise our heating, we've got to worry where that electricity comes from, and in particular, the time value of the electricity. So electricity going forward, even if it's generated from excess renewables, certainly won't be free. So how do we get more bang for our buck? Well, using electricity directly, certainly is what we would teach our students, is something we shouldn't do, because if you have a unit of electricity, you could always put that through a heat pump, and you could get more heat out, Q, than you put in with electricity, E, if the COP of the heat pump, the coefficient of performance, is bigger than 1. And typically, you'd expect a COP of 2 to 3 for a decent heat pump. What's surprising is that in industrial systems, you can get heat pumps that can deliver heat to 160 degrees C. And the reason you can do this is it's not just the heat delivery temperature that's important, but also the lift, the source and the sink temperature. And on the right here, you can see a graph of, that I've taken from a study that shows the distribution of heat that's available from processes, the cumulative heat demand in the EU 28 from different processes. And what you can see here is certainly up to about 160. A large amount of this process heat you could potentially target with heat pumps. Now, domestic heat pumps, you won't be able to do this with, but industrial heat pumps, as I say, because they're able to take heat from other places, potentially can reach these kind of temperatures. Now, one thing the process industries has that the domestic situation doesn't have with heat pumps is we have waste heat. So here we have the equivalent distribution of waste heat in the EU below 200 degrees C. And although heat pumps, if you're pumping from, say, -10 or from the air at 20 degrees up to 160, are going to be very efficient. If you can target waste heat sources, then suddenly your waste heat starts to have much more value than it otherwise would have. So there's a view that going forward, some of the process heating might come from better heat integration using heat pumps. So traditional heat integration will try and use the waste heat, but it won't pump the waste heat from a low temperature up to a high temperature using heat pumps. And that's something that, although it's expensive, is one way of targeting this low temperature process heating sector. So just to finish off, let's have a look at the UK flowchart and see what would happen to these bars if we did the things that people are suggesting. So if we look at, for example, low temperature process heat and drying and separation, if we were going to just replace these with primary electricity from wind turbines with direct electrical heating, then effectively the bars would stay the same and we just have to find more wind turbines to cover the width of the bar. And that would be a big change to the system, but not a massive change. You can see the width of the bar wouldn't change. If we use heat pumps, we'd be able to shrink those bars, say, by a factor of a half. Right? So we'd be able to lower the process demand by a half. We'd be able to use less electricity, and we need half as many wind turbines. If we were going to use something like hydrogen, well, hydrogen going forward is, if it's green, is likely to come from electrolyzers. They only have an efficiency of 70%. So each of those bars will go up or will expand by a factor of 1.4. So none of this is, in terms of the overall macroeconomic scale, particularly difficult when you compare it to the order of magnitude of effort needed to, say, hit these sectors, but it's still a massive change and it will be very expensive. If we think about the high temperature process heating, this is things like furnaces and mineral processing, well, then you either have to use direct primary electricity or you use hydrogen. So you can't use heat pumps to target these things. So overall, we see that the UK is important, but it's not massive. It's not a massive part of the UK energy system. It's a large sector, but there are other sectors that are larger in magnitude, and so as they're going to be much more difficult and challenging to decarbonise than some of these sectors in terms of total quantity of electricity, total quantity of energy available. There are challenges to electrification, and the first is going to be that electricity is not free, despite what people say about free renewables. And the issue that we're going to have to face is dealing with this time-varying production from renewables. And finally, heat pumps might be attractive for low-temperature heat applications, but they're very expensive. And going forward, it's likely that low-quality waste heat is going to become an important resource. So with that, I'm going to hand over to the next speaker.
Great, thank you very much for that, Stuart. I'll just share my my screen, and if you could confirm that you could see that, I'd be grateful.
Yep, we can see it.
Perfect. Well, thank you very much for joining us on today's webinar. Much appreciated, and thank you also for that that thought-provoking presentation. Moving forwards, when it comes to the uses of heat in different industrial applications, well, we appreciate that steam is a very attractive source of energy. And it's true to say that steam is used as a source of energy across a number of different industrial applications. And that's primarily down to the fact that steam can be delivered and can reach temperatures that are far in excess of that can be reached by other providers of energy, such as heat pumps in certain applications. So, as Stuart mentioned, for those lower temperature applications, heat pumps may very well be an attractive provider of that heat, but there are certain applications that are going to require temperatures that are beyond the reach of heat pumps. In other words, it's highly likely that steam is still going to be relevant in many industrial processes. And one of the reasons why steam is such an attractive carrier of energy is because it's capable of conveying a significant energy density. We can carry far more energy down a steam pipe and therefore down a gas pipe than we can in low temperature hot water, for example, that may otherwise be provided by air source or ground source heat pumps. That essentially means that steam and gas are far more attractive in not only conveying that high energy density, but in order to meet those maximum instantaneous peak demands, when we get a huge requirement for that heat energy first thing on our Monday morning or in certain parts of the process. Other benefits of using steam as a gas, as opposed to the hot water that is produced by an air source heat pump, is the fact that steam is a compressible gas, and therefore when we're conveying that steam at higher pressures, it means that steam occupies a very small volume. In other words, we can distribute the steam around a significant infrastructure with a very small and cost-effective pipe diameter. And of course, because hot water is a single-phase non-compressible fluid, and because it has nowhere near the energy density that steam has, then we're going to need to convey that in a much larger infrastructure. So if we're distributing that heat energy around a significant footprint, significant size facility, then with the removal of that much smaller infrastructure and the replacement of a much larger infrastructure that can accommodate hot water, is going to be not only a significant capital cost, in many cases it's going to be very obtrusive. And then finally, we appreciate that steam is a gas. Well, we don't pump it. The steam will move entirely by itself in accordance with the pressure drop around the infrastructure. We compare that to a heat pump network, and we know that the hot water that is produced is going to be pumped. So not only do we need to install a greater number of heat pumps, we need to install a significant number of circulating pumps to move that energy from the point of generation to the point of use. The problem being, of course, that we're consuming significantly more electricity in order to do that. So moving forwards, then whenever we're working with our client, typically that's going to be an existing steam user. And we appreciate that they're going to be combusting a significant amount of natural gas in order to produce the steam. So whenever we're working with our client to help them move towards that net zero aspiration, the first step that we want to take is to help them significantly reduce that demand for steam. If we can help our client drive down our demand for steam today, then they don't need to burn as much gas, and our cost of steam is going to fall. But most importantly, we're going to be reducing those carbon emissions. So the first thing that we want to do is work with our client to help them reduce that demand for steam today. We want to help them identify where any inefficiencies may be with their existing steam distribution network, because by driving down those inefficiencies, then the cost of steam is going to fall and those carbon emissions are going to fall. In other words, we want to help our client optimize their existing steam system, and these are things that can be done relatively easily today. The next step is, once we've ironed out those inefficiencies, we want to work with our client to embrace routine monitoring, perhaps through digitalization, so that they can act on any inefficiencies that may slowly start to creep back in over the years. And then finally, that's when we can embrace modern technology. We can embrace those innovations that can help us move away from those fossil fuels. We can then start to seek ways in which we can utilize other technologies in order to generate steam. In other words, if we can help our client move away from natural gases, yet retain their existing infrastructure, it's going to be much more financially beneficial for our client. And as Stuart rightly mentioned in the previous presentation, it's highly unlikely that our clients are going to be able to satisfy their thermal energy demands using any one technology. The future is likely to embrace multiple technologies in order for our client to achieve their objectives. So it's vitally important that we give thought to that three-step approach. But the most important step, in my opinion, is optimizing the system that we have in place today. It's highly likely that our client's existing steam system was potentially engineered decades ago, at a time when no one really gave any thought to those carbon emissions, and no one really gave any thought to the cost of steam, because this was at a time when gas was placed at an attractive point financially. So it's highly likely that our client's steam system does have a number of inefficiencies as a result of that initial design and installation. So if we can look at certain areas of our client's steam and condensate system, for example, monitoring the condition of the steam traps, ensuring that the size is selected and installed correctly, it means that we've identified and acted upon a significant risk of failure if they were left in the failed open position. Ensuring that the hot water going into the boiler is held at a high temperature. Obviously, if we've got hot condensate going into the boiler, then we don't need to consume anywhere near as much gas to raise steam again. And the best way that we can do that is by recovering as much condensate in the form of that high temperature hot water from all of the processes around site. Keeping the steam dry. We remember that the drier the steam, the more energy there is contained within the steam. So if we can dry the steam, it means that our processes don't need to consume as much steam, the boilers don't have to work as hard, we're not burning as much gas. Drying the steam, we can do that by a good layout of the steam infrastructure. We can also use ancillaries such as separators ahead of the heat exchangers in order to dry that steam. Insulation. If we can insulate the infrastructure, we're reducing heat loss. We're reducing the steam that is going to condense out in the infrastructure, and therefore the boiler doesn't have to work as hard. We're not combusting as much gas. Configuring the boiler controls correctly, so the correct water chemistry, doesn't mean that we've got excessive energy being put to waste in the form of boiler blowdown. But also we need to remember the fundamentals. That high temperature hot water that exists under pressure, that can contain far, far more energy than lower temperature, lower pressure hot water. So whenever we get condensate that is depressurizing, there's got to be a releasing energy. And that is typically in the form of flash steam. And those flash steam vents can really be a significant loss of energy around our client's site. We either want to reduce those flash steam emissions, or better still, think of a way in which we can recover that heat energy. So these are all steps that we can take very, very quickly, very, very easily, in order to help our client understand how they can reduce their cost of steam and, most importantly, reduce those carbon emissions. So I've put together a very, very quick checklist on the screen. These are some of the steps that we can take in order that we can really optimize our existing steam system. There's a significant amount of inefficiencies if we leave these issues unaddressed. Now, in many cases, many of our steam using clients will already be doing these things, but it just acts as a very, very high level sanity check, just to ensure that we've done everything we possibly can today to reduce our demand for steam and thereby doing the things that we can act upon here and now to reduce those carbon emissions. So the next question really is, well, what's the next step? What can we do next? Well, once we've moved beyond those optimization checks, we really want to ensure that we're maintaining that level of efficiency. We want to ensure that we've got routine steam trap auditing. We want to ensure that we've got routine audits and checks of our energy systems. We want to make sure that those inefficiencies don't creep back in. And in many cases, we're able to help with digitalization. For example, ensuring that we've got the maximum flow of condensate coming back to the energy center at the appropriate pressure and temperatures. Self-automating steam traps to ensure that if we've got a significant loss of energy, that steam being vented into the sky, that we can act on those inefficiencies immediately. So it's really only once we've reduced our demand for steam and once we've retained that level of efficiency that we then want to move forward and look at those new technologies. We want to look at different ways of producing steam. We want to try and move away from that natural gas for obvious reasons. We know that steam is perhaps the most efficient carrier of heat energy. It's just that it's those natural gases, it's those oils, it's those solid fuels that have traditionally been used to generate steam that are problematic. So when it comes to steam generation, we appreciate that we can use hydrogen as a source of combustion. If we combust hydrogen with oxygen, then the byproduct is water vapor. We don't have any carbon emissions. So we can simply cap off the chimney from the boiler. We can remove that natural gas burner and we can replace it with a hydrogen burner. We get a green source of steam. But it's true to say that we really, really do need to give thought to how we're producing that steam. It can be very, very problematic to produce it without carbon emissions, and it can then be problematic to transport and then store that hydrogen. It's only really going to be viable for steam applications if we can electrolyze water very, very close to the point of use and in step with the demand for steam. So Spirax Sarco have actually looked at a number of different technologies. We're a huge consumer of steam ourselves for test and manufacturing purposes at our facility in the UK. We've identified that hydrogen may be viable for many clients, but it's certainly not going to be viable for ourselves for the challenges that I've already mentioned. So we've looked at electric steam generation. One of our sister companies, Chromalox, they've got a considerable amount of experience in generating steam from electricity. And they started off in the States over 100 years ago now, where we appreciate it's been more attractive for steam to be produced from electricity up until relatively recently. But we know what the benefits are in using electricity for steam generation. As Stuart quite rightly pointed out, we're not making the claim that electricity can compare with gas for steam production. It can't. And that explains why one of the very, very first steps that we want to take with our client is to help them optimize their existing steam system and reduce that demand for steam, which is really going to help us keep that demand for electricity as low as we possibly can. If we're able to use an electric steam generator, there are going to be significant benefits for our client. So we've actually in removing one of our three natural gas boilers and replacing it with a standalone electric steam boiler. But that's not always going to be viable for many clients. For some clients it will, for other clients it won't, and that may be down to the reason that, well, we just don't have a robust electrical infrastructure available locally. And we also need to take into account that electric steam generators, they can't store energy. So that means that the electrical steam generator, the electrical steam boiler, it needs to be sized in accordance with that maximum instantaneous demand first thing on a Monday morning. So what we're also able to do is If our client's got an existing natural gas steam boiler, and if it's of a reasonably good condition, it may well be that we've helped our client to optimize their existing steam system. Their demand for steam has fallen, and it may well be that that existing steam boiler is now oversized. Well, just as we can remove the natural gas burner from an existing boiler and replace it with a hydrogen burner, we can do something very, very similar by removing the natural gas burner, removing the smoke tubes from a traditional fire tube boiler, and fitting high voltage electrical elements into those smoke tubes. In other words, we've removed the need for natural gas, we've capped off the chimney because there are no carbon emissions, and instead we're electrifying the existing infrastructure. This is something, again, we've done to one of our 3 steam boilers down in our facility in Cheltenham, and we've also undertaken this on a number of client sites in different process industries around the world. So in other words, this is helping our client retain their existing infrastructure. They've got the same steam boiler, the same water treatment plant, the same pipework, the same processes, but they've essentially decarbonised their steam. I'm just showing a very short animation on the screen at the moment that gives you an appreciation and understanding of how this is achieved. So we've removed the natural gas burner. We've replaced it with those electrical elements, the appropriate switch gear, the appropriate control panels. We don't need those, we don't have combustion gases, so we've capped off the chimney. There are no more carbon emissions. We're able to get the boiler up to the appropriate pressure and temperature quickly and efficiently without a purge. The number of elements in the number of smoke tubes that are running horizontally through the boiler mean that we can get a fully homogenized temperature and we can get the steam up to the appropriate condition very, very quickly. So the benefit for the client is when we've got the appropriate steam boiler, the appropriate condition, when we've helped them to reduce their demand for steam very slightly, it means in many cases we can move forward and help them retain steam on their infrastructure, yet help them essentially decarbonise that demand for steam. Again, it means that we need to be satisfied that our client has got a very robust and resilient supply of electricity. And it also means that because we can't store thermal energy within the steam boiler, it means that it can, from time to time, be a little bit problematic to size the solution in step with that maximum instantaneous demand first thing on a Monday morning. Remember, gas, and therefore steam, has quite often got 4 times the energy present within it than we can get down in an electric cable. So we really do need to ensure that we've done everything we can to reduce that demand for steam before we look at alternative solutions. However, we can also consider what we refer to as a steam battery. And a steam battery operates on the very basic fundamentals of thermodynamics, that if we pressurize hot water and we elevate it in temperature, it can contain a significant amount of energy. For example, if we took a pressurized vessel of water, if we used electrical, either from the grid or from renewables, and if we use that to charge an electrical element and elevate the temperature and therefore the pressure of that water that's in storage, maybe to somewhere around 30 bar gauge, where that water can exist as a single phase fluid at 225 degrees, we can hold that energy in storage until such a time that is required. And when we require that thermal energy, when we require that steam, it can be realized by nothing more than dropping the pressure within that vessel. The falling pressure of that high temperature single phase hot water, it'll result in a partial phase change or a change of state from water to give us steam as a gas. And from then on, that steam can be conveyed around site in exactly the same infrastructure. In other words, we're helping our client retain their steam system. They're just moving away from that natural gas. So when we consider those 3 solutions that we've gone through, the electric boiler, electrification of the existing natural gas burner, and the thermal energy battery, well, we need to really compare them to see what the pros and cons are. Well, batteries, we're all familiar with batteries. We use them in our mobile phones on a daily basis. Fantastic for storing energy. Unfortunately, it can only be used for storing electrical energy. No good to us when we need that thermal energy. But it's very, very good whenever we can use renewables in order to charge the battery. And it means we can decouple supply and demand very, very easily. Steam accumulators, they're often used in those larger process industries that need a huge steam demand at certain parts of the process. Problem with steam accumulators, well, as good as they are at storing that thermal energy, typically it means that our client is going to need to retain some form of natural gas combustion to produce steam in the first place. So great for storing energy, great for that huge instantaneous demand, but hugely problematic if our overall goal is to decarbonise our steam system. Electric boilers, fantastic for producing steam instantaneously. One of the problems is, well, it can't store energy. So that means that any instantaneous electric boiler is going to need to be sized in accordance with that maximum instantaneous peak demand first thing on a Monday morning. And that may mean that we just don't have the electrical infrastructure available to support that. So when we look at the steam battery really brings all of the benefits from those previous technologies together. We can store thermal energy. We can use renewable energy whenever it's available. We can ensure that that steam is produced very, very quickly whenever there's a demand. So that really explains why a steam system of the future is likely to incorporate multiple technologies. We're likely to have an instantaneous steam generator that can produce that base load of steam whenever there's a demand. We're likely to have a steam battery that can produce much larger volumes of steam at certain periods of the day when there's an instantaneous demand. But by doing so, it means that we can ensure that our clients' thermal energy systems are retained. And it also means that we can distribute that steam in exactly the same infrastructure and to exactly the same processes without any costly modifications. So that's myself stood next to a steam battery that we've got in operation here in the UK. Many of you familiar with steam systems may think, well, it looks exactly like a steam boiler, and that's the intention. It's manufactured to the same codes, it's got the same controls, the same safety features. The only real difference is, well, it doesn't have a burner and it doesn't have a flue. Instead, we're charging the hot water from renewable energy thermally over an extended period of time, 8, 10, 12 hours. That hot water is held in storage until such a time it is required. And when it's required, we can release that thermal energy in the form of steam by nothing more than depressurizing that vessel. So the vessel typically is manufactured in very, very similar sizes and capacities to traditional boilers. The one that we're looking at the moment, it's sized to accommodate a capacity of 14 tons. We'd fill the vessel about 80% full of water, so there'd be about 12 tons of water there. On this occasion, the client needs the steam to exist at 120 degrees of the process. So the pressure temperature relationship tells us that if we can pressurize to 30 bar gauge and then depressurize to 1 bar gauge, we can provide the client with approximately 2 tons of steam at 120 degrees until such a time that the vessel will need recharging. But that 2 ton, that's very, very useful for satisfying our clients' peak demand. So we can then have a much, much smaller sized electric steam generator or electrified boiler in order to take care of that reduced base load. Again, explaining the importance of doing everything we can to reduce our clients' demand for steam before we start looking at these newer technologies. So just another quick animation for you that shows you how we pull together the benefits with a steam battery. Whenever our client's got renewable energy available on site, we will use that renewable energy, 100% of it, whilst ever it is available. If our client doesn't have renewable energy at the moment, or if the sun's not shining or the wind's not blowing, then we can use grid electricity. And because we're holding the thermal energy in storage, it's very, very well suited to having our client charge the vessel during the quiet hours of night when we may be at an attractive green energy tariff. So we thermally pressurize the hot water, we hold it in storage until such a time that we need it, and whenever we need to realize thermal energy at our process, we can do so very, very quickly just by depressurization. The water that we use, the steam that's produced, the infrastructure, the processes and heat exchangers, they all remain exactly the same as they would do with the previous natural gas steam boiler. So that really emphasizes that three-step approach that we want to take. Reduce the demand for steam today. By reducing the demand for steam today, and by ensuring that that level of efficiency is retained, then it means that the mass of steam that is required, the reduced mass of steam that's required, can often be provided competitively and at scale through those new innovative products. So I'd like to thank you very much for your time and attendance on today's presentation. I'd like to just hand back to Bob now for closing down.
Okay, well, thanks, Dan. That was extremely interesting. And Stuart, thank you to you as well. Two very, very good presentations and very thought-provoking. The attendee questions section of the website's open, so if you have any questions, and there are a few coming in, please add your questions. I will just very briefly talk about the Process Industries Division's series of events while we're waiting for people to construct their questions. We've got an event coming up on the 14th of December, which is energy transition, geothermal energy, opportunities and barriers for the transition. I'm sure everybody will appreciate there's a fair amount of heat to be had. If you dig down into through the Earth's crust, you'll find a lot of useful heat there. And of course, with ground source heat pumps and the like, we can extract that and use it effectively. CPD points are available, of course, for this event. And the details of that will be with you. We've got another event on this series, which is carbon reduction in heating and cooling in process industry, going to be on the 14th of February. We're still working on that, don't have a title yet, but it will be in the same series. So that's a little bit of advertising. Now, perhaps I can kick in with a question and ask, what about the effectiveness of energy storage systems in terms of how long we can store the energy and what sort of gap they can make up? Because Stuart, you started with a slide that showed some gaps when we haven't got wind, and it all goes a bit quiet on that front. Obviously, we have base load with nuclear and other generation sources, but how long can we store energy? The systems I've seen, hydroelectric plants, there's one in Wales, but it can only really cover a few hours. What timescales are we looking at now, gentlemen?
So is that a question for Daniel?
Whoever gets in first, Stuart, I think.
Well, someone else, there's another question on the chat. Someone also correctly pointed out that there are also grid constraints.
Yeah.
As well. So the whether or not you can get these massive amounts of electricity down the grid does depend on where you are in the system. The honest answer is, if you look at certain scenarios, you could be looking at if there's a massive excess of renewables. In some of the scenarios, you could have maybe a few days in a year, maybe 3 days at a time where you need to store energy, maybe 4 or 5. So you wouldn't have many periods where you're needing sort of weeks worth of energy. But in other scenarios, there are very prolonged periods where you have not enough electricity on the grid, just in terms of total energy and the wind that's available. And then the rest of the grid would be employing energy storage. And if it's, so there you perhaps maybe the other way, it's an opportunity. If you're thermal systems can store energy for a sufficient period of time, you can harvest low temperature, low price electricity and use it later. So really, I think it's the question for Daniel. So what's the capacity? You know, how long could you store your heat for in one of your steam batteries?
That's a really good question, and it's going to come down to a number of variables, such as the design, pressure, and therefore temperature of the system in question, and the grade of insulation that is employed to keep that hot water in storage at a higher temperatures for as long as we possibly can. Typically, I mean, we've got a number of these installed, and if we're using the best possible grade of insulation, then we can potentially keep that at a high pressure and temperature, so there's a lot of steam that is able to be produced upon pressure drop, certainly for in the region of 10-12 hours. But if there isn't that demand for steam, then obviously there is going to be a draw of electrical energy, at which point we need to question the viability of that solution. So it really comes down to ensuring that we've sized the battery correctly. An oversized battery is, of course, going to have a certain inefficiency there. And we've just to pick up on the second point that you made, Stuart, about the infrastructure and the grid. It's a very good question, and this is a challenge that we came across ourselves at our facility in Cheltenham. We recognised that if we wanted to move away from natural gas, there needed to be a significant upgrade of the electrical infrastructure. So in removing 3 of our natural gas boilers and replacing them with electrified solutions, we did need to undertake a significant infrastructure upgrade. And the overall cost of the project in its entirety was in the region of 6 million. Now, we did that for 3 reasons. The first reason was we needed to demonstrate to our shareholders, investors, and other stakeholders that we were essentially walking the talk. We can't talk to our clients about decarbonisation if we're not going to do something very robust and impactful ourselves. The second reason was we want to use this as a roadmap that our clients can use and understand the challenges that we faced in reaching electrification. And thirdly, well, it's just the right thing to do to move away from natural gas. So it cost us £6 million in order to achieve that. And I believe I'm right in saying that certainly in excess of 2 million of that was involved with upgrading the electrical infrastructure that is available to us locally. Now, that's not something that's going to be palatable for everybody, but when we're talking about some of those larger carbon-heavy process industries, it's something that they're committed to do, and it's something that they've got to do, so they can use that as a roadmap to help them understand how they can retain steam and instead generate their thermal energy from electricity.
Okay, thank you, gentlemen. A quick question: is steam battery similar to the steam accumulator system?
Yes, very similar. The only difference with a traditional steam accumulator that you probably know in a lot of industries like the brewery sector, the paper sector, for example, is with a steam accumulator, we're putting steam into that hot water in order to thermally pressurize it rather than electricity. So it's very similar in that respect. The only real difference is it's got an electrical element in it rather than a steam sparge.
Okay, thank you for that. And with electrofit, are there any issues with recertification of the boiler vessel? And an associated question is any indication of the costs of converting a steam boiler into electric boiler and, of course, heat pumps?
Well, every case is unique. It really depends upon it depends first of all on the size and the capacity and pressure of the boiler. It depends upon the condition of the boiler. It depends upon the number of heat tubes that are available in the boiler, because the heat tubes are what enables those electrical elements to be fit into the boiler itself. So if there isn't an appropriate number of smoke tubes, then we won't necessarily be able to get the appropriate number of electrical elements into it. So we really need to look at each individual boiler on its merits. And again, I'm banging the same drum about the same message. It reminds us that one of the first and best things we can do is optimize the existing system to reduce that demand for steam. If we can reduce the demand for steam, it's more likely that we will have the capacity in the existing boiler. If you've got a boiler that was reaching end of life, then it wouldn't be a commercially sensible thing to do. But it really demonstrates that we have got options. There are different steps that we can take to help our client achieve that decarbonised steam.
Okay, thank you. And another question is again for Daniel. Have you considered other forms of thermal storage with higher energy densities, the examples being solid phase change, salt pressurized gas, etc.?
Yes, we have, and yes, we are doing that. We've heavily invested in a company in the Nordics that is, they've got thermal batteries that are using salt. We purchased a stake in that organisation earlier in 2023. I think it's true to say that it's still very early days for us, but yes, of course. And we appreciate the decarbonised thermal energy of the future. The only way it's even going to be remotely achievable is if we employ a spread of different technologies and innovations.
Okay. You both mentioned innovation. How innovative are these things? I mean, we've talked about steam accumulators, steam batteries, and electric boilers. How much of it is actually new, and how much of it is old technology that people just really haven't picked up and run with yet?
It's basic. It's fundamentals, Bob. It's basics. If we pressurize hot water, it contains more energy than lower temperature, lower pressure hot water. So we're not doing anything new here. We're not. It really is. It's basics. You know, we're not doing anything new. All we're doing is finding out how we can employ the fundamentals of steam, incorporate electrical steam generation, renewables wherever we possibly can.
Yeah.
We're just trying to find a way that we can ensure that steam is being produced efficiently, quickly, reliably, safely. So I'd be lying to you if I said it was anything new. It isn't. It's just that it hasn't been widely available at scale, at a commercially viable point up until reasonably recently.
Yeah. Stuart, you got anything to add to that?
No, well, yeah, I mean, I agree entirely. If you look back at what we're doing now with a lot of these industrial problems, is we're looking back to how things were done 50 years ago and having to look at the sort of fundamental methods that we use. So the steam battery is not very different to an accumulator. It's sort of good basic process engineering done well, rather than being having to find new physics. I mean, where we would look for new physics and things is it maybe if you're trying to use hydrogen for heating, which of course is the other option that we've not really talked about. Maybe that will be a subject for another seminar perhaps. But there you're sort of having to invent new materials for the electrolyzers to try and get efficiencies up or improve lifetimes or new membrane materials. But most of the stuff that we're talking about doing, people know how to do, and at least can get it to work.
Okay, thank you very much. A question here, any insight into heat pumps applications that require 120 degrees Celsius to 160 degrees Celsius? So the modifications to existing process equipment is kept to a minimum. So there's one on the list, and I guess it's probably one for you.
I'm only an expert in heat pumps in the sense that I've worked on certain kinds of them, so I don't know much about the ones that go to the high temperature. I mean, they're certainly possible, and they would just have to be designed with the right cycle inside them. The key would be that you have to look at the lift. So it's not just about the 120; it's about where you're pumping the heat from.
Yeah. Okay. Can I ask a very basic question then? Assuming you can have sort of a cascade of heat pumps, so the heat output from one is the heat source for the next one.
Yeah.
And assuming you then get to some fairly high temperatures, not necessarily the highest we might want, but
yes. I mean, there's actually no fundamental. The COP just simply goes down. as you increase the temperature lift. The higher the temperature lift. So I mean, the paper I took the figures from, for example, ruled out anything that had a temperature lift of 100 degrees or more. So they said their figure in that paper was that if you were only trying to raise the temperature by 100 degrees, you could use a heat pump. And there are big manufacturers in Europe who can supply heat pumps that will now deliver up to 160 degrees with maybe 100 degrees of lift. But they won't be as efficient running with that as if they were having to pump over a much smaller temperature difference. The problem with cascading is the more stuff you have, the more irreversibility you get. So daisy chaining multiple cycles together, you'll get the inefficiencies of each cycle cascading as well.
Okay. A very simple question. I think this one, Daniel. What is the advisable source of water for the steam battery? And this is from a gentleman in Africa who I suspect the quality of incoming water can be an issue sometimes. You there, Dan? Can anybody hear me?
I can hear you. We lost Dan.
Good, right. Good. That's a start. Dan, we seem to have lost Dan.
I'm here.
Oh, good. Okay. Did you hear the question, Dan?
I did, yes. And it's water scarcity as much as it is water quality in certain parts of the world as well. So, yes, the short answer is it's exactly the same quality and condition of water as it used in a normal plant steam boiler. The infrastructure is the same. As Stuart mentioned, we're not overcomplicating things here. We use exactly the same. Condition of water. The boilers manufactured to, or should I say, the batteries manufactured to very, very similar design standards. The infrastructure, the heat exchangers, they're all the same. So, but the water quality, we've done a lot of research and testing to see if it can stand up and be robust against lesser standards or qualities of water. The reality is, if our client's already got an existing water treatment plant that they're using for the plant steam boiler, then it makes sense to use the exact same quality of water for the battery.
So the application doesn't require a higher quality of water from what's being used in existing. And I guess if water's a scarce commodity, then making sure you don't lose the water through leakage and waste streams and the like is important to recycle as much as possible, which obviously you talked about.
Yes.
Carbon dioxide air source heat pumps, are they capable of generating steam?
Not well. The ones you buy, the sort of typical ones you get for heating applications, I think they're rated to go up to about 90 degrees maximum output, but they're not. I mean, in theory, you can take a heat pump up to any temperature, but the COP would drop off dramatically, and it's not worth doing. The problem with CO2 is it's running supercritical, so the higher the temperature, of course, the higher the pressure, and so it probably becomes very expensive. I wouldn't have thought you'd have used the CO2 heat pump for those applications, but I could be wrong. Okay,
thank you very much. What about process cooling, gentlemen? In either case, obviously the heat pumps are a fridge in reverse, so I guess there's some potential opportunities there. Dan, anything that your company's doing in the world of cooling?
No.
Okay.
In a nutshell, and I am aware of simultaneous heating and cooling heat pumps, but I wouldn't really be able to pass comment there.
Right. I'm thinking back to one of Stuart's earlier slides when he showed a fair bit of energy usage in cooling, particularly in food and beverage.
Well, one thing you're seeing, I mean, I've seen this in not so much industrial applications, but people are now viewing a source of low temperature heat as a significant resource. So they talk about charging up a cold store, for example, or charging up an area with heat. So if you have waste heat that's previously been thrown away at, say, 30 degrees, then actually there are people now who are thinking about using that as a heat pump source, because it's just so much more efficient. It's so much more efficient to pump heat from 30 degrees than it is from room temperature or air temperature or ground temperature. So yes, I think there'll be more projects where people look at these waste heat streams as something useful, perhaps.
Yeah, joined up thinking, really, isn't it? and we do throw a lot of energy away in things we heat and cool. And thinking back to the days gone by when most large country houses had an ice house. They'd harvest the ice from the ponds in the winter, bury it in the ground, and use it throughout the year. Good. Well, we've hit the magic hour. We're now on 1 o'clock UK time. So I thank the presenters. That's Professor Stuart Scott from University of Cambridge and Dan Wells from Spirax Sarco. I thank everybody for their attention during the presentation, for the questions that you've asked. And we hope to hear from you for the next in this series of events looking at decarbonising heating and cooling in the process industry. So thank you very much, everyone.
Thank you.